Welcome to a lesson with Dr. Powell. Let's look at another way that we could compute the volume of this region that we saw in the last video, rotated around this line right here, y equals -1. And this is going to involve a different type of growth. I mean, before we were thinking about volume growth in this direction, like adding on new washers or cross sections, kind of going like this. This time, let's think about adding on volume as we move outward in our radius. So like volume up to this particular radius away from the axis of rotation, to this point, until we get to the final result. So volume with respect to radial growth outwards. Well, what we do is we kind of think if we need the derivative of volume with respect to radius or radial growth. So we think at a particular fixed radius point, so when radius is fixed, what does the forefront of the volume look like? Growth. Well, look at the outside right here at this particular radius. It's a shell. The volume is the forefront of the growth is an area, and it's just the outer shell here at a specific radial value or radius value. So it looks like this, like a cylindrical shell. And so what we need to do is be able to just find the area, the outer area of that cylindrical shell, and that's the derivative of volume growth with respect to radius. Then once we find that area, that's the derivative of the growth, we simply integrate it from 2 to 4 to find the actual volume, which is the change of volume as we go from 2 to 4, which is the total volume that we desire. Okay, so let's take a look and see how that would work. First off, we need to find the area, that outer area. So we think, well, we see a shell right like this. Let's think about cutting it right here and unraveling it out. It's a rectangle. Right here, the circumference is now the length of the rectangle here. So 2 pi r for some radius, and then h times h. So 2 pi r h is how we compute that area. So let's look in our specific case. Radius is in line with y values because it's vertical going up like this. And so we're going to take different y values to compute our radius. In particular, we'll think about y as being kind of r shifted, or a shift of r. So we can really replace dr with dy and really be thinking of this as dv dy even, which is what we have right here. We're going to be thinking dv dy, just remember that. And when we look at this, let's look at one particular shell. And I've outlined different y values that occur. Notice this happens at a particular y value. The shell happens right here at this one. So I can distinguish, if I'm thinking about radius, I can kind of notate the y value here at -1, because that's going to be the axis of rotation. And then right here, we're just going out to y, which is kind of nice. And the shell happens right at y. So this position is just y. That's kind of nice. So to find radius, we just need to find the difference of y and -1. So y minus the -1 is just y plus 1. That's going to give you your radius. So this r value is really y plus 1. The height is just this distance across right here. We know that from here to here is just x. So this is like x comma y, but this x comma y lives right here on this curve. So this is the relationship between x and y if we're on this curve. So we can just solve for x in this particular equation. Doing so, we get y minus, when we get, bring x squared over here and y over there. So 4 minus y and square root. So square root of 4 minus y is the height right here. So to find the area right here, this rectangle, we simply take 2 pi times the radius, which is we computed to be y plus 1, multiplied by the height, which is root quantity 4 minus y. And we integrate from 2 to 4. And if we compute this integral, we should get the exact same result as we did in the previous exercise. So even though this particular video doesn't have this integral worked out, just mention that a use substitution would be best in order to compute this integral. This is computable if you let u be 4 minus y. You'll notice that, and then so if u is equal to 4 minus y, and then that would mean that y would be equal to 4 minus u if you rearrange this equation. So that means you can replace this y with 4 minus u, get something with u in here. It's multiplied by the square root of u, which you can then distribute in. You just have powers of u, and you're off to a good start. So this would be a nice way to go. U substitution, very, very doable here. This is just another way of computing. Sometimes the integral that you get with cylindrical shells is actually easier than the one that you would with the Washoe method, and vice versa. It could work the other way as well. But this is just a little illustration that we can obtain the same volume by considering the derivative of volume with respect to radial growth instead of axial growth of the volume. Thanks for watching.